answer them on Slack. Our final speaker of the morning is Manodeep Sinha, who will be talking about making all of our code faster.
All of your code's faster. Can you guys, is this working? All right, perfect. My name is Manodeep Sinha. I am a senior postdoc at Swinburne, and it's funded under this PyAstro18 Center of Excellence, which is a 7-year program. We're going to solve all of the questions in the universe, obviously. No, we're not. But we're going to try. I am a simulator, and broadly, I work in large-scale structure and galaxy formation, which is why this is my large-scale structure shirt. Looks like large-scale. So because I'm in large-scale structure, I do simulations, I end up with tons and tons of data. Like at one point, a couple of years ago, on Stampede, which is the Texas supercomputer, I had like a petabyte of disk storage on Scratch, which is not like, so because that's what happens frequently, I have to have optimized code because all of my data are either large or I need to do very frequently lots of things. So a lot of my time goes into thinking about writing fast code. So basically everything I know about writing fast code is here. It's in this GitHub repo. It's called CoreFunc. The objective is to do fast correlation functions, but it contains packaging, testing, everything else. The biggest collaborator on this work was Lehman, who's at CFA, and Andrew Herring and Nick Hand. Nick Hand has actually contributed. Both of them have contributed. Andrew particularly just kept poking me to do the documentation properly, and that incredibly improved the package, right? So the last sentence is that I did this because I had to. I optimized because I had to, okay? This took a lot of time, but the only reason why I did it was the science would not have been possible without doing the optimization. So only do such things that I'm about to show you if you need it, okay? So next, why should you pay attention? So the basic purpose of CoreFunc, at least that's the way I think of it, is if you have asked this sort of question, so you have a list of sources, some array of positions in the sky, in your simulation box, and you need to find out all objects that are nearby, where what nearby is some threshold you know about. If you want to compute a correlation function, you know what I'm talking about. You probably already heard of CoreFunc. And the last one, which is similar to the first point, is that you just have 2 sets of points, and you need to compute all separations. So if there is n1 points here and n2 points here, you just need to compute all separations. Separations here could be 1D on the sky, 2D on the sky, angular, doesn't matter. Then if you answer yes to any or all of these, then you can use CoreFunc, okay? This is the simplest code. This is what the code looks like. It's C because that's what I know. I really am a C person. Python is not my, I know more about the C Python part of it than the Python part of Python. So this is what a correlation function code looks like. All it is a loop over the first set of points, then the loop over the second set of points, which is n1 and n2. You have your ith point and your jth point. You have some distance metric. It couldn't be simpler. This is the simplest possible code to compute separations. The only 2 things, basically, that can change between users is your distance metric, which is how do you define your distance between 2 points, and how you bin. Given distance, you're a pair. Given a pair of points at the separation, which bin it goes into. That's all. Yes, it's simple code. But the problem with simple code is that it's simple, which means you ignore a lot of knowledge. For instance, let's say I wanted to compute separations between every one of you that's in the auditorium right now, but I only cared about people that are separated by less than 3 seats. If what I'm doing here is first computing all of the separations, which is from here to there, and then checking if my distance cut is met, then I'm wasting a lot of my time, right? If I only need to look at a third of my linear volume, then in terms of pairs, I should be looking at 27th of the pairs, right? So this I will come to. The way this code is written is actually quite bad for your hardware. Quite bad. People that attended the tutorial on fast code yesterday might already know. And the third part is this cannot be vectorized. And what vectorized is when you're writing here, you're doing 1 point at a time. Vectorized just means that you're doing 4, 8, 16 points at a time. That's all. There's nothing fancy to it. And the reason why you want to optimize code, this is actually an important consideration. If you have to optimize code, first ask that. But when you get faster codes, you actually move along both of these axes, which is you can compute more, so you can do an MCMC, for instance, so you can get real errors, constraints, and you can solve bigger problems, because now it takes less time to solve it. So now we're going to go into technical detour. Basically, what has happened today, this is why writing fast code requires you to know about the hardware. CPU is here, and your big arrays, these are your points, is somewhere in main memory. It is hard. It takes a long time to get data from main memory to your CPU, okay? And that's what determines your runtime, is how well. So this is what I was referring to yesterday as the CPU being the beast. It's basically a raging fire. Can you keep the fire going? And that's what, the amount of heat you get back is how well the fire is burning, right? How fast your code completes is how well you fed the fire. And that's why you have to be careful about how you use your memory, how you access your memory points. So one lesson to take away is just this. How fast code runs depends entirely on your memory access pattern, how predictable it is, okay? So this is kind of a historical background on how computers have come across, evolved over the past. I would say sometime in the 2003 to 5 region is when the hardware hit some hardware limits. So basically quantum mechanics limits. CPUs do this. CPUs process one instruction, roughly, one instruction per CPU tick. Okay? CPU has a frequency. This is the 2.1 gigahertz, 3 gigahertz clocks you hear about for your CPU. That's the core frequency. Roughly, a CPU can do one operation every time your clock goes off. Okay? So if your clocks kept getting faster, which was the case, because I grew up with 600 megahertz, which was high-end when I was first exposed to computers. And then it just kept going up. It kept going up 3 gigahertz, I think I remember seeing 3.6, 3.7 gigahertz. But then it stalled, never grew anymore. So now, if you want to get more done per clock cycle, you have to think about vectorization. This is single instruction, multiple data, which is process bigger chunks in one shot. Rather than going one element at a time, think of doing 8, 16 elements at a time, right? Memory access, this is we just talked about, is really slow. Obviously, Intel, AMD, ARM, you name it, they know exactly what's going on. So they have designed between your CPU and, like we saw in the things, between your memory and your CPU, there are smaller, so smaller but faster, bigger, so memory is called cache. Okay? So, and the CPU will try to get the data to your, the hardware will try to get the data to your CPU as fast as it can. And the last thing, this is kind of why the clock speed stalled. This is where quantum mechanics messed with us. It's because the power requirement scales as the frequency is cubed. So you could not dissipate the power fast enough to keep your CPU functioning correctly. No one wants incorrect results because the CPU is too hot. Because the power required scales as frequency cubed, now, and for the foreseeable future, what's going to happen is that you're going to get more cores at lower frequency. Okay? So multi-core is here to stay. Think GPUs. The CPUs have gone the GPU way. The GPUs got there first, but CPU is going the GPU way. So I did this math. It is correct, but you can get better performance out of more lower frequency cores. So that's the kind of, if you're getting the data into the CPU correctly, efficiently, and you're using vectorized operations, then you're getting the fluff, so it's the floating point operations, higher floating point operations per clock cycle, which is per watt. So that's what maximizes your efficiency. So fastest time to solution, lowest power consumption. Okay? All right. So now this is the actual CoreFunc stuff. The scripting is all on GitHub. The x-axis is the number of particles. This is an autocorrelation. So the first data set is the same as the second data set. It's easy to go hit on the other codes. So what we did was disabled optimizations in CoreFunc so that it did exactly what the other code does. So this is the lower, so the y-axis is speed up, and this is 1. So anything over here is CoreFunc is faster. Below here, CoreFunc is slower. Basically, across the board, CoreFunc is faster. And this is the lower limit. Okay? By default, CoreFunc will run much faster than that. And there is a bunch of this. The one I would like, Halo tools. I was involved in Halo tools. It's written in Python. This is me trying to help with the Python implementation of CoreFunc in Halo tools. It's still a factor of few slower. So it helps, but don't do it unless you need to. That's important to me. That's why it's there. If you go to multi-cores, then it's the same exact plot. Particles, many particles. So what is it? 5 million, I think. And speed up, and you can see OpenMP scaling. There is one that's 10,000 times slower. This is not a typo. This is real. CoreFunc is 10,000 times slower. CoreFunc is 10,000 times faster. And here's the reasons why CoreFunc is faster. Here are all of the reasons. But so imagine you have some domain across which your points are spread. Okay? But you only care about some Rmax. In this case, I'm just taking a cube, but similar things can be done in a spherical geometry too. And so you can bin up everything in 3D cells of Rmax. Right? Easy. And then, when the blue is the query point, you only need to look at the surrounding cells. And that's it. So now you have used up, so you're doing the search much more efficiently. We store, the second point, we store the particles contiguously so that memory access is much better. And that allows us to vectorize as well. There is hardcore, basically, assembly, portable assembly that's in CoreFunc. And we have OpenMP parallelization. It's like better than 90% scaling out to 16 threads or something. It's a very parallelizable problem. And all of these are required to get you a fast code. Okay? So think about memory access and vectorization are the ones. And this is what vectorization does. So all I want you to look at is that this is the number of points in set 1, number of points in set 2, how fast, what is the gain from vectorization, okay? And you can see most of the places it's 4 to 5, and this is my code versus my code. This is not some other developer wrote, right? So vectorization, vectorization helps quite a bit. Similar things, as I see. And here's the, I'm kind of out of time. So this is the history, why it's there. I created mine. It was fast, but it was private. This is the standard astronomer story. I was at a conference, and I created something for an expert in 24 hours that was 6,000 times faster. That's when I went, oh, okay, all right. We need an open source version, right? And because it exists today, you all can use it. It's now 5 seconds. Here it is. It's all of that. Basically it's tested, it's val-grinded, it's cross-checked with multiple different codes. I told someone how it worked, and their calculation went from, not me, 1 hour, sat down with a grad student, and then their calculation went from this to this. It's true story. I would So you can see if you're computing any pairwise separations that's large enough numbers, you might get good speedups. Oh yeah, this is a work in progress. This is the latest and greatest instruction CPUs. So you get similar speedups. These are my proudest moments, also scariest moments. Like, found a compiler bug. Who finds a compiler bug? I didn't think so. It was always bugs in my code. Compiler bugs, for real. We reported back to Intel, they fixed it. They acknowledged that this was a compiler bug. Like, oh, well, it's scary. Like, this AVX512 stuff I just showed you, I can't actually integrate that code because Valgrind doesn't support AVX512, so I don't know if there are resource leaks. Lead Intel HPC person start CoreFunc. All right, my life is done. And here are the conclusions. It's basically there. It's really fast. We made this open source and flexible for everyone to use. And tell me, it should be easily installable. It's documented, and it's also my highest cited BIM entry from last year. Like, it wasn't me. People just use it. I'm like, what? All right, cool. Did something good. So that's it.
We've got time. Got time for one question.
So the metric you were focused on was flops per watt, right? But the thing probably everyone really cares about is like science per person hour. I mean, given your personal experience going through and doing all of this work, do you think it still made up all the different, right? So you focused on the flops per watt aspect, not the like buy 100 or 600 computers where you could have just gone with one using CoreFunc, but was it really worth it just for you, right? It's clearly worth it for all those other people citing you, but for you, was it worth it?
Yeah, so the the flops per watt is not the real thing. Basically, I don't see it. So for me, I couldn't have finished my project. It took 5 minutes, and the science funding, we needed to run 1 million MCMCs, even on an MPI. It couldn't have been done. I would not recommend anyone else to do this. If you need to talk to me, I can tell you what you need to do. This takes a lot of effort to get to this point. And I think I didn't mention, the CoreFunc comes with Python extensions, so you can just do your pair counting from Python, which is how I use it. So.
All right, let's thank all of the speakers in this morning's session, and there's coffee and snacks waiting for us outside.